Hello, my name is Mehmet Avni Arslan and I'm a secondary CS student. In this video, I examine how the oscillation period of mass spring system depends on two main factors: the mass attached to the spring and the effective spring constant. I begin by measuring the period of a single spring using several different masses, allowing me to test the relationship predicted by simple harmonic motion. After that, I repeat the measurements using two springs arranged in series and then in parallel. These configurations change the effective stiffness of the system, so resulting periods provide a direct way to compare theory with experiments. By analyzing how the period varies in each case, I can calculate the spring constant and verify the expected trends for single spring, series and parallel setups. In this experiment, the equipment used is as follows. First, the rod and vertical supports are used to hold the system stable. A digital scale is used to measure the masses. Two mass values are used in the experiment, a light mass and a heavy mass. These masses are placed on a mass hanger, which is suspended from the springs. The clamp is used to securely attach the springs to the support. Finally, two metal springs labeled Spring 1 and Spring 2 are used. These springs are arranged in a single series and parallel configurations during the experiments. I start with the single spring configuration. One metal spring is attached to the rod using the clamp, and a mass hanger is connected at the lower end of spring. In this setup, two different masses are used, 100 grams and 200 grams. Each mass is added to hanger separately. For every mass, the system is pulled slightly downward and released, allowing the spring to oscillate vertically. The oscillation time is measured manually to determine the. Next, I set up two springs connected in series. Spring 1 is attached to the rod and spring 2 is connected below it. The mass hanger is attached to the lower spring. As in the single spring setup, 100 and 200 gram masses are used. Because the springs are connected in series, the effective spring constant of system is reduced, leading to slower oscillations. The same measurement procedure is applied to record the oscillation period for each mass. Finally, I construct the parallel spring configuration. Both springs are attached to the rod side by side, and their lower ends are connected to the same mass hanger. In this setup, three masses are used: 100 grams, 200 grams, and additional 210 grams. Since the springs act together, the effective spring constant increases, resulting to faster oscillations compared to the other configurations. The oscillation period is measured for each mass using the same method as before. In conclusion, the results of this experiment are consistent with the theoretical model of simple harmonic motion. For all configurations, the oscillation period increases as the attached mass increased, in agreement with the relation T equals 2 pi square root m over k. Comparing different springs arrangements showed a clear effect of the effective spring constant. The series connected springs produced the longest periods, indicating a lower effective spring constant, while the parallel connected springs produced a shortest period. Due to increased stiffness, the single spring setup gave intermediate results. By calculating the period mass from manual timing measurements and analyzing the data, the effective spring constants for the single, series, and parallel configurations were determined. Overall, the experiment trends match the theoretical expectations, confirming the validity of the mass spring model and behavior of springs in series and parallel configurations.